All right, so we move on to elliptic curve cryptography. I'm sure a lot of people heard elliptic curves in cryptography, but since they are mathematical, a lot of people try to avoid this concept. So they try to don't know how it works. So to be honest, in order to do research in this area, you should know a lot of mathematics. That is for sure, you know, for the algebraic geometry and other stuff. A PhD in mathematics would be nice if you want to do research in this area. But in order to understand it, of course, you don't need a PhD degree. The main idea, which I'm going to try to explain in the following slides, will be enough for you to understand how elliptic curves work in cryptography. So let's start with a few pictures. So as you can see at the bottom, there is a general definition of an elliptic curve. So elliptic curve is just a geometric object which you can define as y squared equals to x cubed plus ax plus b. So here a and b are just constants, and depending on how you choose an a and b, the geometric definition of the elliptic curve becomes something like one of these. So for instance, if a equals to -1 here, and b equals to 1. This is how you draw this curve on the real plane. So here x and y coordinates are real numbers. Of course, if you use complex numbers, then an elliptic curve actually turns into a three-dimensional object and would look like a donut, a single hole inside it. And actually, due to a single hole, we will call it a genus 1 curve. And there are other concepts like hyperelliptic curves where you have more genuses, but again, this is beyond the topic of this lecture. So, why do we use elliptic curves? So when I described the discrete logarithm problem, and when I also explained the algebra for cryptography, I told you that the hardness of the discrete logarithm problem actually depends on the group, the algebraic group you are working on. So elliptic curves comes into play here because using the points on an elliptic curve, we can define a very strange group with a strange addition operation. So points on an elliptic curve generates a group where the points are the elements of the group. Addition of 2 points P and Q is defined as the point as follows. Draw the line that passes through P and Q. It interacts the curve at the third point R. Multiply the y coordinate of R with -1. The resulting point now defined as P and Q. So I'm defining a new addition operation on the points of a curve, and it is something like this. So this is what makes it a group. So recall that in order to be a group, we have to have an identity element. And in this scenario, the identity element is a point at infinity, which is at the top of the y coordinate. So it sounds a little bit counterintuitive, but this is why this happens because we're working with affine coordinates. When you work on polar coordinates, this definition makes somewhat sense. Okay, so let me explain all of these concepts in these pictures. So assume that your elliptic curve is something like this, but it can be also something like one of these, okay? It doesn't always have to be like this. It doesn't matter, but it is easier to think on this kind of elliptic curves. So let me define how the group operation works. So let's start with addition of 2 different points, P and Q. So assume that you have 2 points P and Q on the curve. So as explained here, you draw the line that passes through these 2 points, and recall that only one line can pass through 2 different points. So it has to intersect at a third point. This comes from the definition of the elliptic curve. So instead of this point, simply reflect it with respect to the x coordinates. In other words, multiply the y coordinate with -1. So just reflect it and say that, okay, this is the addition of these 2 points. This is how we define addition. So we say that the identity element is at infinity. So when you want to add the identity element, for instance, if you want to add identity element to P, since it is somewhere at the infinity, like at the top of y coordinate, you draw the line with P and that thing. So you draw a vertical line. So it passes through the identity element at the infinity, P, and it also intersects at another point here. And, you know, since an addition, we multiplied with -1 and obtain it. As you can see, I obtain P back. So adding P with a point at infinity gives you P back. So minus P is actually this point. Because now if you add these 2 points, you know, you draw the line that passes through minus P and P, it intersects the curve at some place at infinity, we say. This is why we call it, this O notation, the point at infinity. Of course, sometimes you might want to add the point to itself. Instead of adding P to Q, you might want to add P to P itself, because in a group, you know, we can add an element to itself. In this scenario, you draw the tangent line, passes through that point. It intersects the curve at another point. Again, take the reflection with respect to x coordinates, and this is what we call 2P. So now you can add P to this point like this, okay? And this would give you 3P. Or if you add 2P to itself, you would obtain 4P. So as you can see, we can add the point to itself many times, and actually this is where we are going to define the elliptic curve discrete logarithm problem. But don't forget that this 2 times P, actually here the multiplication is not a real multiplication, okay? This is a scalar multiplication, because this is important, because sometimes people talk about elliptic curve point multiplication. This is not a multiplication, this is addition. We are adding the point itself, and in our notation we have a scalar notation here, so that this 2P or 10P is not multiplication of P with 10, it is just adding P to itself 10 many times, okay? These are important. All right, so elliptic curve crypto systems were independently invented by Neil Koblitz and Victor Miller in 1985. And they said that we can use this group for cryptography. Of course, if you draw the elliptic curve like this, as I said, in real coordinates, this is the picture you get. But recall that we, in cryptography, we don't work on groups or fields with infinitely many elements. Here we have infinitely many points. But since we are going to work with finite elements, we have to define it over some group or field. In this picture, we are only considering the points of this elliptic curve whose coordinates x and y are elements in Z8 and 9. So only this many elements remain. And geometrically, by the way, there is no relation between these 2 points, okay? Here we are drawing the points in coordinates x, which are element of Z89, okay? So, I mean, this point does not mean this point. This is what I'm trying to explain. So with this many points, we can work on them, so we can define the discrete logarithm problem on these points. So this is what we are going to use. So let's move on. Elliptic curves over Fp. This will be the field with P many elements, where P would be prime or sometimes a power of prime. So most standards which specify the elliptic curve cryptographic techniques restrict the order of underlying finite field to be an odd prime, so P equals to a prime Q, or a power of 2. So here our field becomes 2 to the m. So in other words, you can either choose a prime P, a very large prime P, or you can choose 2 to the power m, which here m is somewhat large. What we are trying to say is that in practice, you can also use something like this. Instead of choosing a prime or a large prime or a 2 powered, you can choose like 5 to the power n. But this would complicate things, because this way we can have, you know, a lot of different elliptic curves which defined on different fields, but have the similar properties. So standards try to avoid it. So they either stick to the power of 2 or a large prime. This is what I'm trying to explain. So let's focus on this case where P is prime and it is larger than 3. So it's an odd prime, it is not 2. An elliptic curve E over FP is defined by an equation of the form y squared equals to x cubed plus a times x plus b, where a and b are elements in the field FP. Here, in order this to be an elliptic curve, this equation should not hold, which means that 4a cubed plus 27b squared should be different than 0 modulo p. Okay. This is important. This is one of the first things you need to check if an elliptic curve you are focusing, I mean, with the choice of A and B, you have to check if it is an elliptic curve by checking if this equality holds or not. So the sets EFP are the points, consist of points x, y, where x is an element of P and y is an element of P that satisfy this equation. So if we go back, this is what we did here. So these are the points, but also we need the identity element. So we add the special point or, the point at infinity. So in order to visualize what is going on, let's give a very basic example. So let's choose the numbers really small, like P equals to 23. And this is a prime number. And consider the elliptic curve y squared equals to x cubed plus x plus 4. So as you can see here, I choose a equals to 1 and b equals to 4. So first thing is to check if this is an elliptic curve. So let's calculate 4a cubed plus 27b squared. It's equals to 436. But over our prime number 22, modulo 22, it is different than 1. So it's different than 0. If we go back to definition. Since this is not 0, this means that A is indeed an elliptic curve. So now let's focus on the points of this elliptic curve. So there are 29 points on this elliptic curve. One of them is the point at infinity. So the remaining 28 are as follows. So you can actually check it like this. Since we are focusing on P modulo 23, so first thing you need to check if there is a point on this curve where the x coordinate is 0. So you put x equals to 0, you end up with y squared equals to 4. This means that y can be either 2, like here, or minus 2. But minus 2 means 21 modulo 23, right? This is why we get 2 points when you fix x equals to 0. You do the similar thing. You write x equals to 1 here. So it turns out y squared equals to 6. So now you want to check which number you multiply modulo 23 and obtain 6. So it turns out the numbers are 11 and 12. Similarly, you write x equals to 2. It turns out that y squared now becomes 8 plus 2 plus 4. So it becomes 14, right? So you want to check which number is multiplied to itself and becomes 14 modulo 23. It turns out that there is no such a number. So this is why you don't have any point here with the x coordinate equals to 2. So this way you can do one by one. Of course, this is the brute force method. You can do it. But this is for a basic example. If I choose P equals to a number that is like 300 digits, trying one by one would be a very hard process, right? It would consume a lot of time. So we need to have a way of counting the points on an elliptic curve in a fast way. This is the idea. Because the number of these points actually gives you the number of elements in your group, right? So in order to have more security, our elements in the group should be large. This is why we want to have a way to count the points on an elliptic curve. So how we can calculate the points or count the points on an elliptic curve. So these are actually, as you can see, are references to very old publications. So we start with a Scoof paper from 1985. So in that paper, presented a polynomial time algorithm for computing number of elements, number of points on the elliptic curve, where the field defined as fq. The number of points on an elliptic curve over fq indicates when q is odd. So when q is a very odd large prime, we had a polynomial time algorithm to count the number of points in a very fast way. Koblitz, in the second paper in 1991, extended it to the case when q is actually the power of 2. Okay. Scoop's algorithm is rather inefficient in practice because, we choose Q is larger than 2 to the 256. These algorithms, now called Scoof, LKS, Atkin, shortened as C algorithms, received many improvements so that suitable elliptic curves can be generated in a few hours. For one of the recent papers, it's more than 20 years old, but in this area, one of the recent, you can check Sato's paper and see how this point counting works. But, in practice, what you do is just choose the modulus, like here, Q equals to 2 to the M, or you choose a very large odd prime. Then you choose A and B and check if that elliptic curve have enough points that are suitable for you. Of course, in order to do that, one can do it beforehand and, standardize it, and then you can use it. This is why if you go to NIST, you will see some standards where they define many elliptic curves on many different fields so that you can use one of them. So we defined the group operations in a geometric sense, but if you want to write in the more mathematical way, we have the identity element point at infinity. So if you add it to a point on the elliptic curve, it also gives you the point back. So if P is a point with coordinates x and y, then x and minus y is the inverse of those points. So if you add them, you obtain the point at infinity, as I showed you on the pictures. But we saw that we said that we can add P to Q by drawing the line and so on. But of course, in practice, you are not going to intersect these lines with the line and so on. In the computers, we need to have a mathematical definition for that. So it works like this. If P is different than plus or minus Q, P plus Q, which would have the coordinates x3 and y3, are computed like this. So using the coordinates of P and Q, you can obtain the coordinates of P plus Q with these operations. So depending on the field you are working on, these are actually going to be field operations. So as you can see, in order to add 2 points, perform a single group operation, you have to do some subtractions and division and squaring and so on. But when you want to add the point to itself, now we don't have Q here, we are adding P to itself. Of course, P should be different than minus P because otherwise you would have the point at infinity. The 2P is calculated as follows. So here, instead of having Y2s and X2s, because we don't have Q, we give the definition only using X1 and Y1. Okay, this is how you add a point to itself. All right, now we have the group operations. Now we can move on to discrete logarithm problem and then talk about how we can use it. So to give an example to these group operations, again, let's go back to our example. This elliptic curve defined over F23. We counted the elements. We observed that there are 29 points. Important thing is that this is a prime number. So in these scenarios, this elliptic curve becomes a cyclic group, and any point other than the identity element is actually a generator of this elliptic curve. So it is a good practice to check if an element generates the group or not, but what you can do is as follows. So as an example, just choose the first element I gave you, 0 and 2 as the x and y coordinates. If you add this point to itself by using these formulas, you will see that 2P is actually this point. Now what you can do is that adding this point to this, now we have two different points, then we are going to use this formula and obtain 3P. If you continue this way, you will realize that you are actually generating all of the points on the elliptic curve until you add P to minus P and obtain the point at infinity. This is how actually everything works, okay? Now we have the group, we have the generator, so I can define what a discrete logarithm problem on this case, okay? Before moving on, let's give a final example. Bitcoin's elliptic curve. So this is a very famous elliptic curve, SEC P256K1. So Bitcoin uses this elliptic curve as it is defined in standards for efficient cryptography, SEC. You can find the PDF from this webpage from Certicom Research. And that elliptic curve defined is like this. It is y squared equals to x cubed plus 7. As you can see, here we are choosing a equals to 0 and b equals to 7. And it is defined over fp. Here p is chosen as the prime number, which is actually calculated like this. So 2 to the 256 minus these values gives you a prime number. All points on this curve are valid Bitcoin public key. So actually, whenever you send Bitcoin to somebody, actually you are sending your Bitcoins to a point on the elliptic curve. Actually, hash of it so that the address looks somewhat smaller. So in hexadecimal notation, this prime P actually is written like this. Base point G on this elliptic curve is chosen like this in hexadecimal notation, and the order of G is n, and it is this. So this base point actually generates this many elements. As you can see, this number is less than P. So our prime P is somewhat larger, but the group generated by the base point G is a little bit, slightly smaller than this number. Actually, you can choose a number less than P, but not covered in this group, so that, it is not a valid point on the elliptic curve. Okay, so as you can see, in practice, we are working on huge numbers. So as you can see, compared to our example with 23, in practice, we are using huge prime numbers like this. So one thing to recall, actually, this elliptic curve is not included in NIST standards. This was a deliberate choice by Satoshi because some people didn't trust that NIST or NSA. So he tried to choose an elliptic curve that is not generated by, American standards. So this is why he chooses this elliptic curve. Since it is, implemented in Bitcoin, following cryptocurrencies most of the time use the same elliptic curve. For instance, Ethereum uses this elliptic curve too. So this is why it is somewhat important. All right, so in the slide, this is what I actually say, because this is a well-known misconception. For instance, I'm quoting from a book which is published very recently by Wiley, and there they say that Bitcoin uses the SEC P256K1 curve defined by the National Institute of Standards and Technology. And if you just Google, you can find many blog posts saying that Satoshi chose this elliptic curve for no particular reason, but actually he deliberately chose that it is not standardized by NIST. But since this curve is used many times in like the cryptocurrencies and so on, NIST now is considering to include it maybe to an appendix of their next documentation, next standard, so that people can use it for interoperability. Okay. So this actually gives us the main idea behind elliptic curve cryptography. Next step is to define the discrete logarithm problem on these group operations and talk about elliptic curve digital signatures.